Hello everyone, my name is Don Baldemecca. I'll be doing a presentation on Prim's algorithm for CSC 338 taught by Professor Farahani at National University. Okay, so first and foremost, Prim's algorithm is a greeting algorithm, and according to the text, that means it is feasible, locally optimized, and irrevocable. Feasible meaning that it satisfies the problem constraints. Locally optimized means that it is the best solution only considering the local problem. It does not consider the optimization of the problem beyond the scope of the local constraints. And irrevocable meaning that it cannot be changed in subsequent steps of the algorithm. So this algorithm is used to find the minimum spanning tree within an undirected connected graph. From the graph, it takes the list of vertices and weighted edges and creates the smallest weighted tree. So this algorithm is best used for problems like the traveling salesman problem. So the text provides pseudocode as well as a data set for this algorithm, and I'll be using the pseudocode and the data set provided, give a brief walkthrough of the code, and explain how this algorithm actually works. Okay, so a graph of nodes, G, is passed into the algorithm here. And G consists of a list of vertices as well as a list of weighted edges, and the algorithm processes all this data and returns a minimum spanning tree ET, which is a list of edges. Okay, so this is the data passed in. We have the vertex list V here, which contains the vertexes and their index number, as well as the edge list here, which contains the edges, which is the vertices, as well as the weight of the vertices. And the textbook actually provides a visual representation of this data. Okay, so the algorithm initializes a new vertex list, and this vertex list is called VT, and it starts with any vertex from the initial vertex list, or it can. In this case, in the pseudocode case, the code actually calls for vertex V0, which, if you remember from the previous slide, is vertex A. After this, it initializes an empty list, ET, and this empty list will hold the value for the minimum spanning tree we are trying to find, and this list, once filled, will be returned at the end of the function. And you can see that here in these lines. The vertex list is created, it is inserted with the V0 of the initial V list, and the edge list, empty edge list, is created here as well. Okay. So after this, it starts an iterative process. So it creates a for loop that starts from from the value 1 and ends at the value of v minus 1, which is 5. It goes from 1 to 5. Okay. So in the iterative process, the algorithm compares the edge values to find the minimum value of the weighted edges. where the first vertex pointer v must be in the vertex list vt. Now from the previous line and the previous slide, the only vertex in vt is a. So the edges must have a at the v value. So all the edges must have a as the first vertex. And the second vertex pointer u must come from a resulting sublist of the difference between the initial vertex list and the new vertex list. So the difference between the initial and the new vertex list is listed here, which contains these vertices. So the only edges that the algorithm is looking at are edges where A is the first vertex and one of these vertices is the second vertex. From that, we find this edge list here. It then picks the edge with the smallest weight. It allocates an edge pointer E, and it makes E point to that vertex. You can see that here. Find minimum edge E with pointer V, pointer U, where the edges V is in VT, so in VT, and U must be within the difference between V and VT. So it can only be one of these. Okay, so once that edge is found, the smallest edge, it updates the VT vertex list by adding the second vertex U, which was pointing at B, to the list here. And then it updates our minimum spanning tree, ET, with that edge that was pointing, or with the small edge, which is here. It was pointing to AB. And it does this for, again, total 5 times. So these are the steps in the iteration. So you can see here, it will go through all the A and all these values, as well as all the B and all these values. So this actually finds that the smallest edge is here at a BC. Then it adds C to the new vertex list, and it adds BC to the minimum spanning tree list. And again, it does it here as well, where it goes through all the possibilities of edges, where this is one of these values is the first vertex, one of these values is the second vertex, and it finds the smallest one. And it actually ends up finding that the smallest one is FB or BF. So it takes this VT value with this vertex and the resulting sublist, and it uses that as the smallest edge. It takes the F vertex and adds it to VT, and adds the BF or FB edge and adds it to ET. Again, the same logic here. It goes through all these possibilities. It finds that the smallest is EF or FE, adds E to the VT list, and adds FE to the ET list for the minimum spanning tree. And for the last iteration, it does the same thing, same logic, and it finds that the smallest is from F to D, and then adds the D to the VT value, or the VT list, and the edge FD to the ET list. So this is the final ET list, or the minimum spanning tree, which goes from A to B, B to C, E to F, F to E, and F to D. You can see that here. A to B, B to C, B to F, F to E, and F to D. So that is my presentation on Prim's algorithm. Thank you very much.